Very good afternoon to one and all. Uh, welcome you all the students on this last live interactive session on the week 12 in on NPTEL online course certification course on mass transfer operations. So this is the last week. For the next week, I think so we will be doing some revisions and the final exams will be happening for the same course on the NPTEL. So this is the last week. What we have to do is the last module of the uh, entire course as per the NPTEL 7 portal. So we'll go through that. Uh, so before that, its course has been offered by Professor Vishnu Mandal. He is a professor in the Department of Chemical Engineering at IIT Guwahati. And I'm Rashpur Shubham Ajkumar, and as I'm taking your live interactive sessions every weekend, that is on Saturday 3 to 4, and I'm PMR scholar in the Department of Chemical Engineering at IIT Madras. So this is the last week of this course, and which is the 12th week. So we'll be going through some of the concepts which has been discussed during the entire week on the NPTEL SWAM portal, and we'd like to solve some of the numericals based on the concepts as well as some MCQs, and then we'll wind up this entire course uh, for your examinations. So it's better that in the last session also I told to go some of the topics that has not been covered. Please let us know. Although I didn't receive anything, but it's like I think you're getting what I'm saying, right? So please go through all the lecture notes as well as the live interactive sessions what we have covered every weekend. It will be better for your examinations also. So this week tell that's the 12th week, talks about four different concepts. The first one is the packed distillation columns. The second is the introduction to multi-component distillation and multi-component press distillation columns. So like multi-component distillation, so the earlier we, till last week what we have discussed is based on the batch distillation, steam distillation, relic distillation, and differential distillation columns. But here what we are going to discuss is for the multi-component press distillation or multi-component distillation columns as well as the packed distillation. And the fourth topic is the minimum number of stages required and the minimum reflux in the multi-component distillation. The same concept is the minimum reflux and minimum number of stages required for separating the gas and the vapor. Okay, and multi-component batch distillation. So this entire Victor module is based on the multi-component batch distillation as well as the minimum reflux ratio and the minimum number of stages required to separate as well as the packing on the distillation column that is called as packed distillation column. So the last week what we have discussed is that the Ponchon-Savallit method and for the example of the distillation column and the assumptions of the constant molar overflow it's not required in that case, whereas in the Mercavitile method constant molar overflow is required. And another thing that we have discussed in Ponchon-Savallit method is the enthalpy and the energy balance equation is the mu add-on in Ponchon-Savallit, whereas in the case of Mercavitile energy or enthalpy balance is not required, and it gives a real number of the identities. So before we go, we'll start with the design of the distillation impact towers. Okay, so distillation of a liquid mixture in a packed tower is preferred in the following cases. So liquid mixture in a packed tower is preferred in the following cases. So the first one is vacuum or low pressure operation. So the first one is vacuum and low pressure operation. Sorry guys. Second one is the low capacity or the feed rate, you can say, is the feed rate. C is the allowable pressure drop, or the small allowable pressure drop, you can say. And D1 is the corrosive surface. Okay, so distillation in the pack tower is similar, like a pack tower or for distillation is essentially similar to one for use for the gas absorption. So pack tower essentially similar to one used for the gas absorption, or we can say the gas absorption columns for gas and the liquid. However, the tower should be provided with a distributor for the feed at the appropriate location in terms of the pack towers. So this is in addition to the distributor of the reflux at the top. So this is what we have in addition, is that the tower should be provided with a distributor for the feed at an appropriate location. Besides a condenser and reflux drum and a revolver. So if you generally look at the figure of the distillation column, it's similar to the same. So suppose this is the feed tree, you can say as location F, and if I say Z, F, Z, F, and this is the rectifying section. Here there will be a condenser, there will be a reflux drum. Half a portion is reflux and half is taken out distillate as is T into XT. The vapors, so this is a boiler, this is vapor, and this will come out as residue, that is W, XW. And this is the rectifying section, and this is the stripping section. This is what how the design is. So there are two methods for determining the height of the packing in terms of the pack distillation column. So we'll just write it right here right now. Two methods for the determination of the height of packing. So the first one is from the height and the number of the transfer units, that is Hg and Mg. This is height and number of transfer units, and the second is from HETP, that is height equivalent to the theoretical plates. So to derive the design equation for the calculation of the pack height based on the HG, refer to the figure. The figure can be explained the same. So we carry out the rectifying, the stripping section, material balance, component balance, and on the basis of that the final equations are given. It's already there in the notes, but I don't want to derive each and every equation as of now, because this is the last lecture and we want to solve some of the numericals for the same also. So this is how do pack tower, and you need to determine the particular equation. So what I will do is that I will write the specific equations used for determining equation of the operating line, like similar for the Macalethile and constant stability matter, we have an operating line equation for the equilibrium line. So the equation for the operating line for the rectifying section can be written as minus kx dash a upon k dash plus k into y minus yi upon x minus xi. So this is somewhat the equation what we got after like deriving the basic fundamentals like angular mass balance, component balance of the gas and the liquid in the packed out distillation column. So I think so. This is already mentioned in the lecture notes. I don't want to go into deep detail, but it's better like uh, you can identify all these things. So what we do is that we'll try to see some of the concepts how this exchange happens. So the mass exchange between the vapor and the liquid phases in the distillation is most controlled by the vapor phase resistance. Thus, for the state of the accuracy, it is advised to calculate the pack height using the gas phase transfer coefficient. Okay. So the following the procedure described earlier, it is possible to combine the heights of the individual transfer units to obtain the height of overall transfer units. So there is another term like we have already have these equations 1 upon capital K dash y equal to 1 upon small k dash y plus m upon k dash x. And similarly, we have 1 upon capital K dash x, 1 upon small k dash y, 1 upon small k dash x. Okay. So if we see ht of OG is equal to of ht of G plus mg by L HTG. So I'm writing these equations from the already derived functions. I'm not going to derive it from the starting point. Similarly, height equal to critical plates of the liquids can be written at HTL plus L upon mg. This is the slope of the operating line into HTG. Okay, so if I combine all this, what we'll see is that m equal to m dash equal to m double dash. Okay, and this is slope of straight equilibrium curve. So similar process can be used to determine the packing height of the stripping section. Okay. So what we'll do is that so this is for the lecture 38. So out of the 4 lectures, lecture 38 talk about this. Apart from this, we have other concepts also. So what we'll call as the multi-component distillation. So now we'll start with the multi-component. Then we'll go on solving some numericals. So multi-component system is it's a 3-component system. First of all, so the graphical treatment possible using the triangular diagram. So we can say the triangular diagram because it's a 3-component system. The second one is more than 3 components. Graphical treatment is very complicated. So if there are more than 3 components, this graphical representation will be very critical or difficult to represent. Is difficult. From a practical point of view or the practical application point of view, liquid phase can be assumed to be ideal. Raoult's law is applicable for this. and equivalent data can be obtained from the pure component. Okay, so this is called like the basics of the multi-component distillation. So the overall approach to solve the multi-component distillation problems is that same in many respects as that of the described for the binary systems that we have already discussed in the previous lectures also. So there is one mass balance for each component and enthalpy balance are similar for those of the binary case. Okay, so it's similar to the binary distillation column. So the equilibrium relationships are more complex for the multi-component systems. In particular, to identify the most volatile component may change with the temperature in the system. Equilibrium data can be used to calculate the multi-component bubble points and the dew points, or you can say it's necessary. The equilibrium data is necessary or can be used to calculate the multi-component bubble points and dew points. So the limiting cases of the total and the infinite reflux applies to the multi-component columns just as to the binary systems. So it's similar to some kind of like the binary system only. Okay, so we will go through one of the topic which is called as the number of the distillation tower. Okay, number of distillation tower. So in terms of binary distillation, one layer is used to separate the components A and B into relative pure components. So I just write it up. And in terms of the multi-component system with n number of components, or number of fractionators will be n1 fractionators, or you can say as the fractionators are required for the separation. For an example, we can say the three component system are there. So if we say three component system are there, so how many number of the columns or the towers will be required in the distillation tower? So we can say the number of component is three component mixture it requires. So the n minus 1. So this will give 3 minus 1 equal to 2 columns are needed. Okay. So the design calculation method and somewhat for the multi-component distillation, we are not going to discuss it right now. What I will do is we'll directly solve the some of the numericals, but before that we'll go through some of the concepts like what is equilibrium in multi-component system. I'm not going to the design calculation process. So equilibrium in multi-component systems. So experimentally, Bailey data not known in the multi-component system. So what it's not known in the sense it's not known in most of the multi-component system. So experimentally, Bailey data not known in most of the multi-component systems, and is generally computed from the available equations or the calculations. So the Bailey data is calculated from the generally computed from our equation or correlations. And the ideal behavior may assume to be as so that the Raoult's law is applicable. So the last one is the hydrocarbons or the homogeneous series from nearly ideal solutions. So these are some of the concepts and some of the example in which multi-component distillation can be used is the hydrocarbons of a homologous series from nearly ideal solutions. Okay, so this is like for the multi-component system and what is the concepts behind that. Now what we'll do is that we'll solve a numerical. So the numerical is like this. So a mixture of hydrocarbons containing 32 percentage of the N-hexane, 38 mole percent of N-heptane and 30% of N-octane is to be distilled to obtain a distillate product with 0.05 mole fraction of N-heptane and a bottom with 0.05 mole fraction of N-hexane. The column operating pressure is given as to us as 1.2 atmosphere. The 40% of the feed is to be vaporized. Calculate the product composition and the minimum number of the ideal plates. So this is like the one of the numerical I wanted you guys to just see, and it's also there in the lecture notes, but we'll try to solve it out. If there is any problem, just let me know in between. So we can see which is the there are three components can be given, that is n-hexane, n-heptane and an octane. So we can separate this into three different components, that is the light key, heavy key, and heavy most key components. Heavy key or heavy non key. Light key, heavy key, heavy non key. So if you take like the if you go through the question, we can see that the light key is an hexane, heavy key is an heptane, and the heavy non key is an octane. Okay, now we make some assumptions here before we start to proceed the solution of the problem. The first one is a no octane is in the distillate. Okay, so the octane is to be distilled to obtain a distillate product 0.05, that is the 5 mole fraction of n-heptane and a bottom with 5 mole fraction of the n-hexane. So we make that no n-octane in the distillate. The second one, 0.95 mole fraction of n-hexane is in the distillate. Okay, we take the basis as 100. Per hour of the feed rate. So you can take any basis, it's just I'm taking 100 for the convenience of for solving the problem. So we carry out the overall material balance or overall mass balance. You can say F equal to P plus N D plus W. What we usually write is W, that is the residue. Therefore, 100 we have considered as a molar flow rate of the feed, and D plus W. Now we don't know the distillate and the residue fluid, so we write in terms of one thing, that is if the residue is 100 minus T. So this is 1, you can assume. Now carry out the hexane. So we are defined with T given components, n-hexane, n-heptane, and n-octane. So we carry out the, first of all, we carry out hexane mole balance. So F into XF equal to D into XT, W into XW. So F is given to us as 100, and hexane in the feed is given as 0.32%. It's equal to distillate. So we have written D in terms of W also we can write, right? So distillate and the W. So distillate is given as for NXN is 0.95 into D. Fraction of the NXN in the distillate is given as 95%. So we can write as 0.95 XT into D plus W we can write as 100 minus T into XW, that is given as 5%, that is 0.05. This comes out to be 32 equal to 0.95d plus 5 minus 0.05 d. Therefore, d equal to 27.19 equal to 30 mole per hour, and W equal to 100 minus D equal to 100 minus 30 equal to 70 mole per hour. So we have got like D. So this is the distillate flow rate, and this is the velocity flow rate. Okay. So the composition of the bottom product can be calculated using the following conditions. So we'll just write it out. So we compose all the n-octane and all but 0.05% of the n-heptane and 0.05 mole% of fraction of the n-hexane. So what we'll do, we just create a table. So we'll write the key components. We'll write the compound. Then we'll write the feed mole fraction. We'll write distillate into xt. We'll write xt also. W into xw, xw, and ki at 102.2 degrees Celsius and 1.2 atmosphere pressure, that is given to us. Okay, so if you go through just like light key, heavy key, and heavy non-key components, what we have written previously, so it should be MC6 and C7 and T8. So the feed is given to us already as this is F into S, that is 32, this is 38. So we have calculated for the light key component, we have already calculated in the previous term. Like similar wise, you can calculate for all the things. I'm writing down in the form of a table, that will be easier for all you guys. So D into S is 28.5, 0.95, 3.5, 0.05, and this is going to us 2.0s. Similarly, you can find out all these things. I'm just filling it up here. You can derive the same things like carry on the mass balance and a material component balance. For is the light key, sorry, heavy key, light key we already done. You can carry out for the heavy key and the heavy non-key in the similar ways, like you solve for the hexane one, like this one, and hexane. Okay. Zero, zero, 30.429.42, and sorry. Sorry guys, my system is hanging. Just 1 minute, I'll just rectify it. This is not wrong. This is double. Yeah, so we are here. So distillate is 30 and residue is 70 and feed is 100. Okay. So in order to determine the number of the minimum number of the plates, what we'll do is that we know that the equation, the Fansky equation, okay, we'll just write this equation. Before that, we'll find out the alpha. Alpha we can be said out 2.08 upon 0.92, that is y by x equal to 2.26. And if we calculate the n minimum, that is a Fansky equation, is given as log of xd into d divided by, so this is the light key and the heavy key, so you need to take care of both the things. X of t into d into x of hw w divided by x of ln into w whole divided by log of alpha of light key into alpha. Okay, so we'll just put all the values here. So log 195 divided by 0.05, this is 0.05 divided as 0.521, all divided by log of alpha, that is 2.26. Or this can also be written as log of x of ld x of lw divided by x of hd by x of hw whole divided by log of alpha l. Okay, so this is x actually, not alpha, it's just x of hd. So if you put all the values, what we'll get is that log of 0.95 by 0.05 is log of 19 divided by 8.096 divided by log of alpha 2.26 equal to 5.288 divided by 0.815 equal to 6.5. Okay, so this is what we got as the minimum number of plates required for distillation column. And similarly, like the minimum reflux terms, that the minimum reflux equation are based on the invariant zones around the feed where the composition stops changing. So this is the another term. So like we already saw, is for the multi-component distillation column. And like another topic which was discussed in the this week was based on the multi-component distillation with minimum reflux ratio in that same multi-component distillation. So in order to determine an approximate minimum reflux ratio is to represent a multi-component mixture as a pseudo binary system. So I'll just write for just like minimum reflux ratio to determine an appropriate minimum reflux ratio is to represent a multi-component mixture. As a pseudo-binary system. So this is done by creating a hierarchical feed made up of the two key components only. So in terms of the McCabe construction, we can use B to determine the pinch and the minimal reflux ratio. So this is somewhat like to determine an upper minimal ratio is to represent a multi-component mixture as a pseudo-binary mixture. It is this point you need to determine for multi-component system and the minimum reflux ratio. So similarly, it is also having its own concepts and all the things and some numericals based on that. But all what we'll do, we'll go through some of the MCQs so that it will be better for you guys to understand much more in deep way. So this week is somewhat based on this multi-component distillation itself and some of the numericals for that. But I think so as far as the distillation concept is concerned, McCabe method is the far most being asked in the final examinations, and somewhat why Ponson-Servet method has been used and how to you solve the numericals based using the Ponson-Servet method and their assumptions, why Ponson-Servet method is different from McCabe method, and this term comes, it's called a multi-component distillation. That's more than two components, so that you can three component system or that n component systems. So the number of the towers required for the multi-component distillation column for the separation of gas and the liquid in terms of refineries or some other plants. You can consider if there are 10 components, the number of the towers or the distillation columns required will be n minus 1 fractionators, that is 10 minus 1. So I'll give an example. If there are 10 components, you want to separate how much distillation columns will be required. So n minus 1, that is 10 minus 1 will be 9 columns distillation columns will be required for the separation. So this much what we have discussed today. Apart from this, we'll go to some of the MCQs before being closing this entire course for a final examinations. So we'll go to the first one. So the distillation in the packed tower is preferred. So there are four options that are given, and we have been asked for the packed tower distillation in the packed tower. So distillation in the packed tower is preferred, and the four options are given to us as for so the first one is for vacuum or very low pressure operation, for low capacity or feed rate, for small hour pressure drop, and for all of the above. So if you can see in the pack tower, there will be a packings and there will be a pressure drop when the pressure build up inside the packings due to some diametric problems. So the allowable pressure drop should be small in terms of the pack distillation tower, and it has a low capacity or the feed rate because it's a packed tower, and then the packings also occupy a space between the gas and the liquid flow, and for the vacuum or low pressure operations. So the packed towers is predominantly used for the low pressure operation or for the vacuum operations, and it has been used for the low capacity or the feed rate. So the feed rate has to be very low, or it has to operate not has to operate at a low feed rate, but the capacity has to be the low. And it has to have a small allowed pressure drop because the packings are there, and if the packing pressure drop is high, then it will ultimately lead to the detrimental problems in the distillation column, which may reduce the efficiency of the separation of the gas and the liquid. So the appropriate answer is all of the above. For the packed distillation tower, it has a low pressure drop. It should have a low pressure drop. It should be used for the low capacity of the feed rate, and it can be used for the low pressure operation or for the vacuum operations. The second one is for multi-component systems. Underwood equation gives. So there are, like for the multi-component systems, we have gone for the Fensky equation. Similarly, there is an Underwood equation which gives the minimum reflux ratio. So this one you have already gone to the lecture notes. So this you must remember this equation, what is Underwood equation, and when we are going to use Underwood equation. So if in the numericals they show or they give you guys to determine the number of the determine the minimum reflux ratio, so you must use the Underwood equation for that. And if you give the minimum number of the stages required for separation in the multi-component distillation, you should use the Fensky equations for the same. Okay. So the third equation is similarly for what we have discussed right now, is that Fency's equation gives minimum number of trays for minimum reflux, total reflux, any given reflux, or none of the above. So the Fensky equation has been determined for the number of minimum number of trays for a case of a total reflux. It's not for the minimum reflux, but a case of a total reflux. So we assume total reflux while solving the Fensky equation, which gives the minimum number of trays. So the correct answer for the Fensky equation, which gives the number of trays for the total reflux ratio, not for the minimum reflux. The last one is This is the average relative volatility alpha AV is given as. So we can see that alpha is given as y by x mostly, like the vapor to the liquid ratio. And you can see here average relative volatility alpha AV is given as alpha of the top. So now here there will be two different products. So there's the top and the bottom. So if you consider what will the relative volatility if the if you want to find out the correct option from this is alpha top by alpha bottom raised to zero point 0.5 or square root of this thing. So I think this is the straightforward question, and you can straight away say that it's the alpha relative volatility is given by relative volatility of the top components, but the multiply by relative volatility of the bottom components, square root of that, that is square root will be zero point 0.5. So the correct answer is this. Okay, so this is are some of the MCQs we have discussed from the assignment problems, and there are some also numerical assignments. I don't want to solve it because its due date has not been ended. But what we discussed today is that what are packed distillation towers and how they are similar to the batch distillation. Apart from that, we also discussed what are multi-component distillation columns, minimum reflux ratio for multi-component distillation columns, and we have discussed some one numerical based on that. Apart from that, we also discussed some of the MCQs for the same concept that has been discussed during the entire week. Okay, so this is what we have for the course as well as from the last week of the week 12. And I thank you all the students who joined this course and attended the online live interactive sessions. It's been a great pleasure to like solve some of the miracles which have never been solved in the live interactive sessions one-to-one with the undergraduate students all over from India. And I thank you all once again for attending this course and attending this online live interactive sessions on NPTEL Swim portal. And I hope you guys will learn a lot from this live interaction sessions as well as from the NPTEL Swim portal. Is the best portal to learn to go in India. So I wish you best wishes for the final examination also. So I hope you guys will fly out with great colors and go out with good marks. So all the best and best wishes for the final examination. Make sure you go through each and every concept from the week 1 to week 12 once again before starting for the final examinations. You have 2 to 3 weeks, I think so, or most probably 2 weeks, I think so. Plus, please go through all the lecture notes plus the live interactive sessions that we have been solving from the past week 13s. And I think so it will be helpful for you guys to crack the final examination with the high fly curves. So all the best and thank you for joining this live interactive sessions. Thank you guys. All the best for the final examinations. Thank you. Signing out. Thank you guys.